Thank you, Jonathan. I think you're absolutely right. Naming a project, a new innovation project, is probably one of the hardest things you have to do. Because if you don't get it right, it can be awful. I want to introduce our next two speakers who are coming up together. Firstly, it's Tim Flower. Tim is the railway maintenance professional, specializing in technology adoption to enhance asset reliability and efficiency. At Network Rail, he led the development and rollout of the PLPR and secured £190 million for the Intelligent Infrastructure Programme. He joined Connex in 2021, initially leading the UK market before expanding to Northern Europe and international business development in 2024. And Rob Lacey. Rob, with 26 years of experience in railway infrastructure engineering, Rob brings a wealth of expertise in maintenance, asset management, R&D, and standards and control. He began his railway career as a senior technical officer at Bedford. So there's a few stories to share, where he gained hands-on experience in track maintenance. Robert managed processes, assets, innovation, and currently he's the route infrastructure engineer for Anglia. And I'd like to welcome you both on board to talk a little bit about your project. Thank you.
Hi, everybody. Brilliant. So, yeah, thank you very much for having us. Thanks for organising such a great event to the PWI as well. Really, really enjoyed it so far. So Tim Flowers, Mona introduced me. I'm just here to talk a little bit around our systems and how that will then hopefully link to what Rob's going to talk around in terms of taking boots off ballast, hopefully forever from a track inspection point of view. So what... Have I missed a slide? Sorry, I missed the slide there. Over eager. So what is our system? Our system is essentially a vibration monitoring device. So we fit it at the bearers, at the switch toes, or at the crossing nose, or as close as we can get. We can also put it into plain line if there's a requirement, for example, on longitudinal timbers, and various other solutions. What we do is the device sleeps until the trains come along. As a train gets towards it, it recognises the vibration, wakes itself up, and then measures the vibration of each axle as it passes through the crossing and the switch. The device then goes back to sleep until rinses and repeats all day long until about 2 a.m. It sends the data off. All of that data is then processed, so it's then ready for the engineers as they come in the following day. We also have a point machine solution that I'm probably not going to go into detail about today, but essentially there's loads and loads of point machine data in Network Rail. We can reprocess that data and give additional insights against it to give greater prediction and diagnosis of potential faults. So we're trying to, I guess, provide as much insight around the switch and crossing as is possible, but based on our own data and also bringing in existing data, for image data, for example. Hopefully we'll bring in track geometry data one day as well, so we can start to really bring that together and give a fully holistic view of what's happening at the switch. In terms of why us, why are we different? So there's lots of solutions out there that can measure voiding, but the big thing that we see is the insights that are available from the acceleration measurements that we do. So we've got a very, very high-end accelerometer. We sample very, very high frequency, and that enables us to give different insights to others that we see on the market. And from the analysis we've done, we believe around 50% more defects are identified through acceleration than from voiding alone. From analysing RDMS and FMS data, so rail defect management system and fault management system data, where our devices are fitted, we've identified precursors to 80% of broken crossings and 78% of all closed crossing defects. Open crossing defects are a little bit harder because quite often they can be quite minor, but as they grow, we start to identify them. So when they get to the point where they need actioning, that we generally find around 70 to 80%, which is great. And we don't expect to find them all. There's certain defects that just aren't recognisable through vibration. From a failure perspective, from a delay minute perspective, the system is really effective. These numbers are much higher than we expected, because obviously there's lots of things that can go wrong in S&C that have got nothing to do with vibration. The relays, the interlocking, there's all kinds of things that could occur that cause the points to fail. But from the analysis we've done, 65% of the delay minutes had some kind of precursor indication. So again, that's really huge in terms of performance of the railway. So hopefully, as we get more and more systems rolled out, we'll begin to really make a difference on that, on those failures. And unsuccessful maintenance is really easy to identify. So we are very successful at that because you can see the asset's got worse or it's got better for a week. So that's a really good indication that the maintenance that's being applied either isn't being applied properly or it's the wrong maintenance for the asset. So hopefully that can bring a cultural change over time. People start to think, let's not just go and lift and pack it. Let's think about the root cause and let's fix that root cause. And also it supports reliable centre maintenance regimes, which Rob will talk about. What was that? Didn't work. There we go. So in terms of where we are currently, in Network Rail, we've sold around 1,900 devices. We're in every single route, some routes more than others. So West Coast South, East Coast, Scotland, Wales have all taken a significant amount of devices, and we're starting to grow into other routes as well. So we're starting to get a really good asset population, which enables us to obviously build more insights and understand more around what our device is able to tell the engineers, which obviously grows its own momentum. So we're really, really pleased with the coverage. We do really want to push on with getting the devices installed. So if anybody's got any devices in the office, please put them on the ground because you will get benefit from it. And that's something we're really pushing on. Previously, up until now, for concrete bearers, we have glued the system. All being well, by the end of April, we'll be able to drill into the concrete bearers, which provides a much faster and better solution for the device. So we've submitted our paperwork, so we should be getting project acceptance in April. So that will be, again, a big step forward and makes the installation process so much better. I just want to talk around some of the more in-depth insights. So from a acceleration point of view, what is good and what is bad, there is no standard around it. The faster the trains go, the higher the acceleration. So how do you put a threshold on the acceleration? Because at 50 miles an hour, 5G could be really bad. At 100 miles an hour, 7G might be all right. So we're trying to work out how do we give better insights based on that acceleration, because the absolute values are useful and do provide indication, but what works on Sussex probably is too low for West Coast Mainline, because 100 miles an hour versus 125 miles an hour. So that difference is considerable. Crossings have different wheel transfer lengths and different rates of load transfer. So we need to take that into account. We need to take what's the crossing constructed of? Is it timber? Is it wood? And the train speed is really important. So we create the relative acceleration for every single train. So that so we calculate the speed of every single train to about probably 5 to 10% accurate. Sorry, 90 to 95% accuracy. And we use all that information to give a relative view on how high the acceleration is. So if it's at 0, that essentially means that's the norm. That is, for that crossing, that's behaving right in the middle of all the crossings of that angle, that construction type and that speed. If it's 100%, we start to say that's quite bad. So that's twice as bad as the norm. 200%, we're saying, you've got serious problems. Some of the assets we see do have around 400, 500%, and they nearly always break. At switches, the acceleration is much lower. So you always get high acceleration at a crossing in a switch because the wheel transfer area, let's say always, nearly always, there are some really bad switches as well. So we need to set we need to understand what's the difference there. So 3G at a switch is probably really, really bad, and you're almost definitely going to fail probably in the next couple of months. So again, you need to understand where the device is fitted to get the most out of the system. And what relative acceleration does is brings all those factors together to give a really good prioritization list, which is ultimately what most engineers ask us for. They want to know what to do next, and we're able to do that. So you can see the difference there in that crossing angle is really significant, and that makes a massive difference to the trajectory of the wheel. So here we've got a moderate absolute acceleration of 7.8 G. So in Sussex, that would be actionable. You'll be out there next week. On West Coast Mainline or wherever, I'm sure that one is, it's probably okay. But the relative acceleration is 423%. And that is driven because it's a really, really low line speed. So I think the line speed is around 50. We've done site inspections, and there's a misshapen nose, which is which is, I guess, causing and caused by the high impact forces, because obviously it's the worse it is, the worse the impact force is going to be, which is then going to make the crossing worse, and so on and so on and so on until it ultimately breaks. And at this one as well, the displacement is around 4 mil, which is not, it's high, but it's not massively high. So this asset is in very poor condition, but using traditional methods of monitoring, it's okay. So it's about finding new insights on the assets that enables people to respond preventatively. And then this is our newest feature, which I think we're very excited about. So this is reconstructing the vertical wheel trajectory as it goes through the crossing. So we want to bring in the specific railhead condition and ultimately get to calculating the impact force of every train as it goes through the crossing. So we've built a kinematic model combined with the acceleration, and that together reconstructs the passage of the wheel through the crossing, which hopefully I can sort of illustrate here. So the device is fitted here, the train's going through the crossing in this direction, so it comes in, goes through the design dip, and should, in theory, come out smoothly. But what's happening is, because you've got a defect, you're getting a secondary dip, which shouldn't be there, and therefore you've got a defect that probably needs actioning, and that will get worse and it will grow because of the forces that are going to be impacting on it. So we've now released this for, I think, probably a good proportion of our crossings. We started off at the highest speed, and then we're gradually working our way down with the models, and I think now we're around 50 miles per hour. We've got some really nice examples that we can obviously show if anybody's interested afterwards, where before it's really, really bumpy going in and out of the crossing, and they've replaced the crossing and it's really incredibly smooth. So you can see what a great job they've done as part of that maintenance, but also what a state it was in before. And that is obviously ultimately going to delay trains if it does crack, if it does break. Just some examples. So the first one is relatively good. There is a minor defect, but it's nothing major. Obviously, could probably do with some kind of weld repair to treat it. The second one is obviously really, really, really bad. So the train's coming in really steeply. So there's material missing here, but also it's coming out extremely steeply and then lifting off, bouncing, lifting off, and then bouncing again. So again, it's got that cyclical effect, which will eventually cause more and more and more damage. And what we've been able to do is turn that into dip angle. But obviously, lots of you will know that dip angle is really a proxy for force. We use dip angle because we couldn't measure the force. We're now able to calculate the force to a pretty high degree of accuracy, and that will then help us to build whole life cost models, so on and so forth, so we're able to predict how much remaining useful life each crossing has got. And the final bit is we've linked with one big circle, but we can link with any imagery really, as long as we've got the geographic location that Jonathan just alluded to. So if we can pinpoint that, we can then say, here's the downward facing images, here's the sideways on facing images, so that people are able to do a initial check. You can't do a full scoping obviously from a camera, but you're able to see, what is happening in that crossing. Do I need to go out urgently? Can I wait a little bit? So on and so forth. So it reduces travel time, it helps decision making, and streamlines the maintenance efforts. So again, that's one part of going towards this holistic switch. That's really our vision, giving all the information possible about a crossing. Thank you. I'll hand over to Rob.
Yeah, I'll take that. Nice one. Nope. That one. No. That one. Yep. Nearly. Thank you very much. Can everybody hear me? Yeah. So Rob Lacey, as Mona introduced me, I'm currently the route infrastructure engineer for Anglia. This first slide it's an introduction to an outline business case that I've put together over the last 6 months for automated reliability centered track inspection. Bit of a mouthful. We call it ARC-TI, which is a bit shorter and a bit easier. Probably missed out. Maybe need to have a C on the end, and we could call it Arctic. But It's an Eastern program, and its primary goal, as stated up there, is to remove boots from ballast by the end of CP7, and that's by leveraging technology to replace track inspection, and that's both basic visual inspection and supervisory inspection, and using that same technology to undertake scoping and verification activities as well. Before I go on, it's worth noting that I've removed any reference to any of the companies we're referencing and working with at the moment. We are test bedding a lot of the ArcTI concepts on the 153 and using that as a bit of a sandpit for feasibility and such around the concepts we're using. And the reason I've removed all the names is because at some point in the not too distant future we'll be going out to tender, and I don't want to. I want to be utterly agnostic and make sure that we get the best range of solutions out there to meet our specifications, but don't end up prejudicing anything along the way. This program, in essence, is a necessary response to some of the larger recent changes in Network Rail that are aimed at removing red zone working, the introduction of more intensive timetables, with the inevitable knock-on of reducing the amount of access that we get. The wholesale move to nighttime inspections, so you're getting a less quality inspection probably, and also a direct challenge from Paul Rutter, who's East Coast route director, who was leading the modernising maintenance program, and his challenge was to take staff out of harm's way, and i.e. remove boots from ballast. So at a very high level, the program aims to enhance safety, performance and cost efficiency in track inspection by identifying 400 functional failures that we've identified in the track system, and using technology to detect precursors of those functional failures, replacing the traditional track inspector or Mark 1 human eyeball and size 9 boots, whatever, and those display staff, as it were, would be moving to, instead of inspecting and noting down faults, they would be actually fixing the faults and making an actual difference to the asset that they're maintaining. So, how does it all work? So, working left to right. The first jigsaw piece, as it were, up there is a picture of a standard that I penned a few years ago. It's NR L2 TRK 7014 for those that are interested, and basically it's Network Rail's risk-based maintenance standard for track systems. In truth, it should have been called Track Reliability Centered Maintenance Standard, because that's really what it's based on, but risk-based maintenance was the buzzword at the time, and so that's what was used. But reliability centered maintenance, and that was the concept, and it builds essentially an optimized maintenance plan for the track system. Within the standard, we've created a FMECA, or a failure modes and effects and causation analysis, and within that FMECA, we've detailed around 400 functional failures, as I spoke about earlier, within the track system. These functional failures are categorized based on their functional impact. For each failure, an evident precursor is required, and at the moment, that is for the Mark 1 eyeball. That's calibrated for the Mark 1 eyeball and some of those tactile inspections that you would go out there. But what we want to do is identify those precursors with technology. And if we can cover all of those 400 precursors with technology, we can cover track inspection. So what we've effectively done with that FMECA is produce a really good and clear specification of what we need to go out to the market with. So we need to identify these precursors to functional failures using technology. We've taken an in-depth analysis into all of these point Ps or precursors, and found that roughly 70% of them are visual in nature. So, i.e., that means they're probably detectable through video automation, pattern recognition, or other forms of artificial intelligence using downward-facing line scan cameras or forward-facing video camera footage. The remaining 30% of those precursors are found using probably geometry. Well, they are found using geometry or remote condition monitoring, or even drones or whatever. But we're quite certain that we can square off and get that 100% of the track system undertaken by technology. Once we've identified a precursor or a point P, we're moving on to locational accuracy. Once we've identified that precursor, we know that the track asset is on the path to failure, and it's important to look at the asset history to estimate the future rate of degradation. To do this, it's absolutely imperative that we have extremely accurate relative locational accuracy, as we need to know that we're looking at the history of the same location all the way through. So we've identified a precursor, we look back at the history, we absolutely need to know that we're looking at the same location each time. Otherwise, we're not building up a rich picture around that point P or that emerging fault. The project's identified technologies that conceive these repeatable and reproducible relative locational accuracy to around about 30 millimeters. So it's a real big boost to the program, and we can and that's even between different machines, because it's about scanning the ballast bed, as it were, and looking for patterns within the ballast bed. Moving on to the next box, we plan to use world-class data analytics and dashboarding software to combine many data assets into many data sets to predict the location's degradation rate and point of failure, and therefore plan effective and timely interventions. Once the degradation rate is established, it will be regularly refreshed and highlighted to the maintenance team if that degradation rate, for instance, changes. And most especially if the current plan suddenly falls outside of the predicted failure time. So, and it will be highlighted, and it would mean you'd have to bring your maintenance forward. Those advanced analytical systems are able to compare similar data sets and draw conclusions and use big data to find relationships in the data that is often opaque even to the well-informed railway engineer. So they are quite powerful in what they do. And then finally, on the last part of the slide, what we're trying to build is we're using Insight, which is an internally developed software to manage the defect management workflow. So from A to B, the section manager and the TME use Insight to take it from the defects inception all the way to the point where it's the intervention, and then look at the intervention. As stated earlier, some of these systems we want to introduce and cannot and should not be 100% relied upon. So these systems will present low certainty candidates to supervisors and engineers to decide, hopefully, about creating virtuous circle by reinforcing that machine learning and basically improving those algorithms. There's the IM program and Insight, two major programs that are ongoing already. So and this slide really, it shows the synergies between the two major existing projects in this field. So firstly, the IM program is developing the next generation of asset data collection, and it should be going out to tender very shortly. As I said before, Insight is Network Rail's trusted internal integrator for our asset management systems, and is designed to be the universal front end for the end users and our supervisors and engineers. With just the IM program and Insight, the end users will be presented and be able to make informed decisions using the asset data produced by the IAM program. However, with ArcTI added to it, there's the surety. It's covering the whole track system for the IAM program, and also for Insight. ArcTI will automate the identification of faults and their degradation rates, and dynamically give a time to intervene. All these three systems together allow us to take boots from ballast and allow us to eliminate track inspection. This one is more for Network Rail people. So you've got IM program down the side, which is all that data collection. So there's some good stuff there, PLPR, track geometry, ultrasonics, UGMS, and we've got ground penetrating radar and all that stuff. Through the middle, we've got Insight and all the things they're doing, presenting data to the end users, the engineers and section managers. In the grey are the things that we want to bring new to the business. So we firstly, within the data collection side, we want to have that enhanced absolute local accuracy, and then going across. Well, I see I've only got 2 minutes, so I better hurry up. And going across, we're introducing the factors I've spoken about already with ArcTI. I'll skip to the last slide. So the benefits. The ArcTI program is primarily designed with safety benefits in mind, and the outline business case for is just for Eastern, the Eastern region at the moment, which incidentally represents roughly a third of the network. So we predict a reduction in 240,000 hours of boots on ballast, introducing this program, the decreased risk of accidents and fatalities among track inspectors. This proactive approach aims to improve overall safety in track maintenance. The project is expected to generate significant cost savings with an estimated return of £92 million over CP7 and CP8 against the development cost of around £44 million. Those savings are both cashable and non-cashable, and I think the cashable benefits are just shy of the £44 million. So through better and more timely interventions, we predict a 5% reduction in service affecting failures. I think that's probably a bit under-egging what we're actually going to go for. Programs like this in other industries have generated improvements of about 15% generally. There's environmental benefits, CO2 emissions, and that cottage industry about driving people from here, there, and every access point known to man. So there's CO2 benefits there. There are many additional unspecified benefits that I haven't put into the business case, not least of which is if all the job banks are automatically filled, you're able to understand and benchmark different DUs against different DUs and actually put money where the asset really deserves it. And so you haven't got the vagaries of this section manager putting everything into their job bank and this one putting just the things they really need to get done. The concept of the outline businesses has been endorsed in principle by the Eastern Region, Eastern Region's Infrastructure Board, and been remitted for further development, look at synergies with overhead line. So this is perfectly in line with overhead line, and also scaling it to cover the whole of the country. So a lot of the developmental costs in here would stay pretty much the same, but a lot of the benefits would triple in nature because we're only a third of the network. And finally, there's a very long way to go. I've just lost my page. There's a very long way to go, but the one thing I know after speaking to so many suppliers is the technology is there, and the suppliers are ready, and the supporting industry is ready. The question really is Network Rail ready? And more poignantly, it's soon to come, is Great British Railways ready? So yeah, that's my presentation.